Hello everyone, my name is Abílio and I will present the work entitled Numerical Modeling and the Prediction of Residual Stresses in AISI 316L and 18Ni300 steels produced by selective laser melting. A special thanks to the team, Marques, Batiste and Nobre, for providing the experimental residual stresses, and the remaining of the team that assisted the numerical simulations, with greater emphasis to Maria Pires and Marco Parente. The content of this presentation will include the framework description of the research, followed by a reference of metallic additive manufacturing. Then a very important part will be the presentation of some experimental details and the numerical details. Afterwards, the numerical results and discussion will be presented. The presentation will end with conclusions and future work suggestions. Another presentation in this conference will give further details about the experimental activities on residual stresses measurements. As a framework for this presentation, we will start with the introduction to the metal additive manufacturing. Then the motivation of this research will be disclosed. Afterwards, the developments of the numerical models will be presented. Then some parametric studies will be shown, namely the influence of different parameters on the residual stresses will be presented. Afterwards, we will perform the analysis of the numerical results and the comparison between the numerical and experimental data will be performed. Finally, the conclusions in the future work will be given. Additive manufacturing allows to go from the CAD model to the final part in a relatively small time, allowing higher degree of freedom and reduces the need for expensive tooling. Nevertheless, it has been used essentially to low-volume parts. Metal additive manufacturing is responsible for significant residual stresses and still is considered an expensive process. According to the ASTM, there are 7 different groups of additive manufacturing, being the power bed fusion and the direct energy deposition the most popular ones for metallic production, with power bed fusion dominating the market. This slide tries to explain how power bed fusion works. A substrate is fixed on the build platform. In order to reduce the oxygen level in the chamber to the desired level, the build chamber is filled with inert gas. A thin layer of metal powder is laid down on the substrate and leveled to a determined thickness using a leveling device, as for example a roller or a blade. The heat source scans the powder bed surface following a tool path calculated from the component's CAD data. This process is repeated in the subsequent layers until the component is complete. Typically, the feedstock could be metal powder or wire. The beam size is in the range of 50 to 400 microns. The scan speed could be in the range of 1 to 10 meters per second, and the edge spacing can go from 50 to 200 microns. Despite not being the main focus of the present research, some preliminary simulations were performed for the direct energy deposition process. Therefore, a small description of the process is present in this slide. A substrate or existing part is placed on the work table. To create a melt pool, the process nozzle with a concentric laser, electron beam or gas metal arc focus on the part surface. The material is delivered as powder through the coaxial nozzle for laser or as a metal wire in a side delivery nozzle. The melt pool solidifies and forms layers of metal as the nozzle moves away at a constant speed and follows a specified toolpath. There is a gas protection and powder carrier which is conducted through the nozzle. Subsequent layers work in the same way, building up the part layer by layer until it is complete. The feedstock could be therefore metal, power, or wire. The beam size usually is in the range of 0.5 to 4 millimeters. The layer thicknesses could be in the range of 0.5 to 2 millimeters. Transverse speed could be between 300 and 2000 millimeters per minute, and a step over between 1 and 2 millimeters is common. This slide illustrates some applications of the metallic additive manufacturing, which includes the tooling, energy, and the medical implants industries. Many of those parts need for post-processing operations, including machining. In order to conduct the research, some specimens were printed using the laser powder bed fusion or the selective laser melting on a carbon steel plate for residual stress measurements using the X-ray diffraction technique, which allows the surface residual stresses evaluation. So one specimen with a prism shape made of 316L stainless steel was produced. For this material, thermomechanical properties from the literature were adopted for the numerical simulations. The numerical simulation of the process took into account the machine settings like layer thickness, laser power, etch spacing, laser scan strategy. In another case, benchmark bridges, according to the NIST suggestion, were produced using a miraging steel. For this material, we adopted thermomechanical properties that were evaluated within the research group. Again, the machine settings were considered in the simulation. Two laser scan strategies were adopted, as will be described later, and besides the residual stresses evaluation for the bridges, we also adopted a deflection analysis after cutting the columns of the bridge. For the prism made of stainless steel, 3 surfaces have been scanned using X-ray diffraction techniques, and you can see on the right of this slide the mesh of points that were measured using this technique. In this slide, I show you again the bridge that was built using the miraging steel. This bridge is attached to a base plate, and during or in that condition, we measured the residual stresses in a set of locations, as you can see on the right picture. And after the residual stresses measurements, we also performed the cutting of the legs of the bridge, leaving attached to the base plate the right part of the bridge. With this cutting procedure, we will release some residual stresses, which yields to a deflection of the bridge that was afterwards measured using a contacting probe. As regards the development of the numerical models, we can refer that those models were built in Abacus using a plugin for additive manufacturing. Progressive elements activation is permitted. The moving of the heat source is performed based on a G-code post-processing. Weak coupled thermomechanical simulation is also allowed. The laser powder bed fusion and the direct energy deposition specificities are allowed in simulations. For example, in laser powder bed fusion, a complete layer of elements is activated, replicating the recoater action. This slide illustrates the first stage of a simulation of additive manufacturing, which consists on thermal analysis. In the slide, both powder bed fusion and direct energy deposition simulations are illustrated. In this slide, the second stage of the numerical simulation, consisting on the structural or mechanical analysis, is presented. In the slide, both powder bed fusion and direct energy deposition simulation are illustrated. Parametric studies were performed aimed to investigate the effect of the mesh size, the scanning strategy, the base plate preheat for the prism geometry. Also, the powder bed fusion and the DED were compared for the same geometry. Regarding the bridges, two scanning strategies were investigated. Besides the residual stresses, for the bridges, a deflection analysis was also performed. This slide illustrates, for the block simulation, a qualitative view of the influence of the mesh size on the residual stresses, being clear that coarse meshes may impact significantly in the quality of the results. Regarding the residual stresses, they were computed for the block attached to the build plate. In this slide, one shows how the mesh size influences the residual stresses on the top plane of the block. One can see a less pronounced influence of the mesh on the longitudinal stresses, and for the transverse stresses there is some influence or some significant influences of the meshes, but we can see some convergence. Now, for the frontal plane of the block, there is always an influence of the mesh size on the results. For the two more refined meshes, there is already some reasonable agreement for the longitudinal stresses. Regarding the preheat effect of the base plate, simulations revealed that between the room temperature and 250 Celsius degrees, there is no significant influence on the residual stresses for the block simulation and for the frontal plane. Still, regarding the parametric study, surprisingly, the simulation of the laser powder bed fusion and the directed energy deposition for the block revealed very similar results, taking into account the expected scatter band for this kind of data. This slide compares the experimental and numerical results for the residual stresses at the top of the block. The transverse stresses are in fair good agreement between numerical and experimental results. For the longitudinal stresses, the numerical result seems to overpredict the experimental result. Regarding the frontal face, and longitudinal stresses for the block, one can see that in general the numerical results overpredict the experimental values. Despite persisting the overprediction, for the vertical stresses the deviations are lower. For the side face of the block, numerical and experimental results are mixed, but numerical results shows the same general trend of overestimation, which may be due to the boundary conditions of the base plate, which was fully clamped in the simulations. For the benchmark bridges, a very refined mesh was adopted in order to allow a proper definition of the bridge legs. Also, a simulation into two stages was performed. Residual stresses were computed for the bridge legs attached to the base plate, and then the bridge was further simulated cutting its legs to allow the deflection measurements. Two scanning strategies were adopted for the bridges protection. Nevertheless, the scanning strategy of the left was simulated for the moment. This slide compares the residual stresses for the bridges, and one can see that for the longitudinal stresses, a proper agreement in the central part of the bridge is verified, but results are deviating for the extremities. Regarding the transverse stresses, the experimental trend was not really captured. Regarding the bridge deflection, there is a very good agreement in the majority of the bridge extension, with one exception for the first point on the left end of the bridge.
Well, regarding the conclusions of this work, different scanning strategies did not influence the prism's residual stresses results in the powder bed fusion model. However, this variable had an impact on the bridge's results, which led to believe that the influence of the scanning strategy depends on the part geometry. Increasing the temperature of the base plate reduces resulting residual stresses magnitudes. A more refined mesh should be applied to the bridge in order to achieve valuable and accurate results. Numerical models promoted higher values of residual stresses when compared to the experimental data, possibly due to the complexity of the modeling process. Additionally, the base plate behavior in the numerical model is different from the experimental study, which can result in the over-prediction of the residual stresses. The numerical results of the benchmark bridge's deflection after leg removal were similar to the experimental data, which is a good indirect validation of the overall residual stresses field estimation. As future work, we recommend to study the results convergence using more refined mesh sizes, study the influence of laser power and edge space on the numerical model, develop a condition that represents the powder bed in the powder bed fusion process and apply it to the existing model, provide experimental data of the direct energy deposition process and establish a correlation with the numerical results. Compare the numerical results to other commercial softwares, and finally simulate and analyze the influence of each treatment in the additive manufacturing processes. Thank you for your time and attention. And I would like to acknowledge some projects like MemTool, Strength, Adding, and Gears 3D. Thank you very much.